Alright. Section 1.2 is on page 12. Talks about row reduction and echelon forms. Echelon form is really important. The goal here is not only to approach it, but to interpret it correctly. A rectangular matrix, matrices look like a rectangle, is in echelon form or raw echelon form if it has the following three properties. 1. All non-zero rows are above any rows of all zeros. All non-zero rows are above rows that are zero. Okay. Each leading entry of a row is in a column to the right of the leading entry of the row above it. Alright. All entries in a column below a leading is 0. And we'll talk about what this means really quick. Now, we have a special. If a matrix in echelon form, so it has to be in echelon form first, satisfy the following additional conditions, then it's in reduced raw echelon form. The leading entry in each non-zero row is 1. So these are the rows. The leading entry, if you move to the right, if it's non-zero, it has to be a 1. And for example, here it doesn't work because that's a 2. That doesn't count. Each leading 1 is the only non-zero entry in its column. So for example, it doesn't work right there. This is not reduced. Here, this is not reduced. And if I look at this is not reduced. And oh, this is not even echelon form. Well, I don't know why I'm rushing and giving the answers. Let's work through those because you might overlook something. You'd be surprised. So let's look at the first problem. First things first. All non-zero rows are above any rows of 0. There's a row of 0 right there, and okay, 1 is satisfied. Each leading entry is in a column to the right of the leading entry of the column above it. So that's 1 right there. And yeah, okay, that one is fine. All entries in a column below a leading entry is 0. That's true. That's true. Okay, very good. What else? The leading entry in each non-zero row is 1. That is right. This is all 0, so that doesn't count. And lastly, each leading 1 is the only non-zero entry in its column. Each leading 1. Oh, leading 1. My mistake. Each leading 1 is the... Okay, yeah, so hey, this is reduced. My mistake. It says each leading. So you gotta look left to right. This doesn't count and this doesn't count. So I might have misspoke. Now let's see the next. If I look at this, does it satisfy these cases? Well, is it in echelon form? First, okay, the first one is fine. There are no all zeros. Each leading entry in a row. This is the leading in the first row. This is the leading in the second row. This is the, so only those 3 count. Each leading entry in a row is to the right of the leading entry above it. That's true. This is, yeah, to the right and to the right. All entries in a column below the leading is 0. That's true. So this is for sure echelon form. Is it reduced? The leading entry in each, let me see, that's 1. Okay, that one's fine. Okay, here's the problem. That's not a 0 and that's not a 0. So 5 is not satisfied. So we say this is in echelon form, but not reduced. If I get to the third one, let's see. That and that. Oh, and that. Those 3. Right? Actually, here. This, and that. So this is not an echelon form. Automatically, it doesn't work. Number 2 is not satisfied. This is not to the right. So that's a problem. Ah, come on. And how about this? If I look at D, that, and that. So this is, and the 0 is on the bottom. That's very good. So that's what you do first. You move the 0 row to the bottom. Second, all the entries in a column are to the right. They are to the right. Look at that. 1, 2, 3. They're to the right. And all entries in any column below a leading is 0. All of these are 0. Those are 0. So yes, this is echelon. But obviously it's not reduced echelon form, because this here has a 1 above it and this here has numbers other than zeros above it. So I wouldn't spread this that much. You just need to get comfortable with this because they use it in a lot of definitions. And let's get started with something very important. Well, first things first, we need to define and we need to understand definitions in this class, as we're going to do work correlating to them, and we want to make sure that we're doing the right work. So, if I look at this, this says uniqueness of reduced row echelon form. Each matrix is row equivalent to one and only one reduced echelon form, which means if I reduce a matrix, I can only get one echelon form. You can't do it one way, get an answer, and do it another way, get a different echelon form. You'll get the same one regardless. This is a very important definition. A pivot position in a matrix A is the location in A that corresponds to the leading one in a reduced row echelon form. So at first glance, you might not be able to tell. You have to reduce it to figure out where those are. A pivot column. So there's a pivot position. A pivot column is a column of A that contains a pivot position. That's very important for our solutions. So if I take this, the goal here is not for you to sit down and spend a lot of time working on those, but it turns out that's the work required. It says row reduce the matrix in 3 and 4 to reduced echelon form. Circle the pivot points in the final matrix and in the original matrix and list the pivot columns. It's very important you understand that. So if I do my math, that is, so anytime I put an arrow, that means I did some work. My first goal is to make that a 0 and that a 0. Multiply row 1 by -3, add it to that row. Multiply row 1 by -5, add it to that row. So again, we're not after just the work. Assume you did that. You got 0, 0. That will be a -4, -8, -12, -8, -16, and -34. And now, if I make that a 1 in the next step, 1, 2, and 3, right? And if I multiply row 2 by 8 and add it to row 3, that will be 8, that's a 0, that's a 0, 8, 24, that's a -10. Right? And now, if I go ahead and proceed, reduced row echelon form, I'm going to make that a 1, divide by 10, so on a test, there's a very good chance I give you the following, exactly what I'm doing right now. So I'll give you a matrix, and I wouldn't show you all of these steps. I'll show you the last steps. I'll show you what that means. The idea is for you, so again, multiply by 3, add it to the second and the third. Oh yeah, that does work. 0, 0, 5, 2, 3, 1, 0, and 1. And if I am to go ahead and... Actually, that's good enough. I don't need to go on anymore. So if on a test I say give you this matrix, put that, and put this matrix next to it. I'm telling you, I used row reductions to really figure that out. Can you tell me where the pivot points are? I could go on and do more. You know, I could make that a 0. But this is more than enough. In this, let me use different colors. In this, do you see the 1 is right there? The 1 is right there. Do you see where the 1 is here? It's very important you get that. So, pivot column 1, 2, and 4. This is column 1, this is column 2, this is column 3, and this is column 4. So if I was go ahead, I'm going to go back to the original. And there's a reason why we do that. You'll figure that out later. You'll figure that out later. For now, just learn what we're talking about. And we are talking about this, and this. So when they tell you those are pivots, they mean if they row reduce this matrix, they will end up with 1s right there in reduced raw echelon form. And you'll figure this out quickly. This really doesn't come to play because it's dominated by the term before it, but we're not going to worry about that. Let's look at the next problem. Let's look at number 8. Find a general solution of the system whose augmented matrix is given. So they're giving us this matrix. Suppose I multiplied row 1 by a -2 and added to row 2. So there's a lot of these things. They give you in the book, and I give you, since this is augmented, now I'm going to do this. You don't have to. Multiply by -2, added 0, -8 plus 1, -1, 0, 0, and -14 and -4 if I'm not mistaken. And if I make that a 0, take and divide that by a negative. There it is. If I multiply this by a 4 and add it to the top, that's a 1, that's a 0, that's a 0. By a 4, that's -16, that's a -9. So what does this tell us? Do you notice this is like saying x, y, and z, but they like x1, x2, x3, which means we have an extra row in there. So how many pivots? There's 1 pivot and 2 pivots. That's for x1, x2. That tells me sort of like x3, the book likes to call it 3, that's fine, I'll tell you what that means. If I let x3 be t, and here they would like to say, well look, if you put it in reduced raw echelon form, then x2 must be a 4 and x1 must be a -9. Again, what this means, you have an infinite amount of solutions, something we're going to be dealing with a lot in this class. It barely comes up in pre-calculus, but here it's all over the place. There's no solution in the infinite. That's always the case. So if you let t equal 0, that's a solution. If you let t equal 1, 2, 3, 4, that'll be a solution to this matrix. What if they gave me this problem? What if they gave me number 14? Well, if I proceed ahead, if you notice, it is an echelon form already. All what I have to do is 0 that out, and pretty much I'm done. So, if I rewrite this as multiply by if I multiply by a -2 and add it to the top, that's a 0. 12 minus 5 is a 7, and -2. 6 minus 6 is 0. That's a stays, and that's not a 5. If I multiply by, what did we say? negative 2. That will be negative, that's a negative 9. There. So in this case, again, this is like x1, if I put a line right there, x2, x3, x4, x5. You look at the pivots. The pivots are 1 pivot, 2 pivots, 3 pivots. So I have 4 of these variables. That's 1 equation, 2, 3, 4, but I have 5 variables, right? So there is a missing indicating x sub 5 is free and x sub 4 is free. Now x, oh, I'm sorry, let me just look at that really quick. I lied. The pivot, do you see where the pivot is? That says x sub 5 is 0. X sub 1, x sub 2, and x sub 5 will have a value. How many are left over? X sub 3 and x sub 4, those are the 3. That's how we figure that out. Cool? Now, I know that x sub 2 isn't that the equation for x sub 2? Doesn't that say x sub 2 minus 6x sub 3 minus 3x sub 4 equal 2? So if you move those over, wouldn't you say that is 2 plus 6x sub 3 plus 3x sub 4? And similarly, if I take x sub 1, I should write that as a negative 9 and minus 7x sub 3, and that would be the actual solution. So later on we're going to be playing with those and say what they mean and all of that stuff. And one way of writing the solution, I mean, this is all they want in this. If I make that 0, if I make that A and that B, I could say that x sub 1 is negative 9 minus, we called x sub 5, x sub 4, x sub 3, minus 7b. And x sub 2 would be 2 plus 6b plus 3a. Two plus 6b plus 3a. Where, okay, third time will be a charm. Where a and b could be any number. But this is what we want for now. So it's important to see where the pivots are to figure out which of those is a 0 and which of those are free. And it makes a big difference. Next problem up is number 18, and let's pay attention and see what we learned. This is an augmented matrix. Determine the value such that this augmented matrix is a consistent linear system. Well, let's see how this plays. If I take row 1 multiplied by negative 5 added to row 2, 1, negative 3, negative 2. If I add by negative 5, that's a 0. 15 plus h. And by a 5, that's negative 5, that's a 10 minus, that's a 3. So, if, think about it, this says, and I suggest you write it until you get the hang of this. If 15, that's x2. If 15 plus h equals 0, then you're saying 0 equals 3. There's no solution. Inconsistent. But if h which means what? H equal negative 15. If H does not equal a negative 15, as long as H is not negative 15, the system is consistent. Consistent means it has a solution. Inconsistent means it does not have a solution. Again, if I write this as an augmented matrix, I'm looking at 1, 3, 3H, and a 2 and a K. And if I reduce it, just choose H and K such that A, the system has one solution, no solution, unique solution, and many solutions. Alright? So let's see how this works. If I multiply row 1 by a negative 3 and add it to row 2. If I multiply row 1 by a negative 3 and add it to row 2, that's a 0. Negative 9 plus H and negative 6 plus K. So everything comes down to really playing with this. And let's see and think about this, not rushing. This says negative 9 plus H times x2 equal negative 6 plus K. My K looks like a 12 right there. There we go. Plus K. Alright. So let's get the no solution out of the way first, because that's what they have. I was going to say let's do the no solution. If it's no solution, right, I want this to equal 0 and this not to equal 0. Because if they both equal 0, that's infinite amount of solutions. I want one of them to be a 0 and one of them not to be a 0. So if I have H equal a 9, that will make the left side 0, and K not to equal 6, then I'm going to get a no solution. Are we clear on that? Hopefully. If not, just think about it. If this is equal to 9, that will be 0 on the right hand side. If this doesn't equal to 6, that's going to be a number other than 0. Right? And therefore you're going to have no solution. 0 cannot equal that. If I want to have an infinite amount of solutions, those are the easiest. So let's do that next. If I want to have many solutions, I will have H equal to 9. I want 0 to equal 0. Right? Here I want 0 to equal to A, where A is not 0. So 0 equal to 0, I must have H equal 9 and K equal 6. That will mean we have infinite amount of solutions. Once you free one variable, you have an infinite amount of solutions. And if I want the one solution case, unique solution, then I would like for this to be a number. I would like H not to equal 9, right? And it doesn't matter what K is. As long, if K equals 6, then you get, say, 5x2 equals 0, x equals 0. That's a solution. If it equals 5, it equals 7, it doesn't matter. So just think about that and make sure that you really digest this information, because we're going to build on it heavily in this class. And that's going to happen for the next few weeks. And there's the homework.